All right, everyone. Welcome to today's Explainer. Let's jump right into the good stuff. If you're an undergrad in computer science, you've definitely heard of AES, the Advanced Encryption Standard. It's basically the gold standard of modern cryptography. But today, we're not just going to stare at abstract math on a whiteboard. No way. We are going to do something way more interesting. We're going to literally track a single byte of data as it fights its way through the entire, complex, mathematical gauntlet of AES.
Here's our roadmap for today. First, we'll establish the physical laws of our digital world with the finite field foundation. Then, we'll track a byte's actual encryption journey, dig into the S-box security logic, see how we forge the expanded key, and finally, figure out how to safely reverse the whole process to rescue our data.
Okay, part 1, the finite field foundation. To really understand AES, we have to grasp its biggest hurdle first. How in the world does it operate perfectly inside strict 8-bit boundaries?
So, think about this for a second. When we encrypt data, we're fundamentally just doing math, right? Adding, multiplying, dividing. But a computer byte only holds 8 bits. How can a computer just infinitely add and multiply data without exceeding that tiny byte's capacity, overflowing, and completely losing the information we're trying to protect?
Well, the genius computer science answer to that is the finite field, specifically GF2 to the 8th. You can think of this as a completely closed mathematical universe that contains exactly 256 elements, just numbers 0 through 255. In this specific field, an 8-bit sequence isn't just a basic number. We treat it as a polynomial. That clever trick lets us perform really complex operations perfectly within our 8-bit limits. Anytime you add, subtract, multiply, or divide two values, the answer simply loops back around to become another value perfectly contained within that exact same 256-element universe.
Look at the stark contrast here. In standard math, numbers just keep growing. If you multiply two big numbers, you need more bits to store the answer, which means wasted bit patterns and overflow. But in modular arithmetic over our finite field, the values loop safely inside those 8 bits, no wasted space. But here is the absolutely crucial takeaway for encryption security. Working in this field ensures that every single non-zero element has a required multiplicative inverse. As you'll see in a few minutes, that is the secret ingredient that makes our encryption mathematically reversible.
Moving right along to Section 2, a byte's encryption journey. Now that we know the physics of our digital universe, let's throw a single vulnerable plain text byte right into the AES gauntlet.
Check out this high-level map of the whole process. Our byte doesn't go in alone. It enters as part of a 16-byte block, which we call the input state array. And depending on whether our secret key is 128, 192, or 256 bits long, our byte is going to face exactly 10, 12, or 14 sequential rounds of intense mathematical transformation. Inside every single one of those standard rounds, our byte has to survive 4 distinct hurdles. First up, substitute bytes, which literally swaps our byte out for a completely different one. Second, shift rows, a permutation that slides bytes around. Third, mix columns, which mathematically blends the bytes using that finite field math we just covered. And fourth, add round key, where we XOR our byte with a piece of the secret key. This visual absolutely nails what happens next. It illustrates a concept called diffusion. Our single byte doesn't just sit quietly in its lane. If our byte enters at position 1, the shift rows transformation guarantees it moves to a completely different column. Then, mix columns guarantees its bits are mathematically blended with 3 adjacent bytes. It spreads like wildfire. After just a couple of rounds, every single output bit heavily depends on every single input bit. Okay, Section 3, the S-box security logic. We're pausing here because this is where the heaviest mathematical armor is applied to our byte. Take a look at this quote from the Rindal developers, the actual creators of AES. They deliberately sought a design with a low correlation between input bits and output bits. Why? Well, if the output is just a linear mathematical function of the input, crypto analysts can literally use standard linear algebra to crack the cipher in seconds. The S-box exists for one primary reason: to completely thwart those simple mathematical attacks. So here they are, the actual S-box and inverse S-box lookup tables. It's a 256-byte grid. When our byte hits the sub-byte stage, its value is used as coordinates to grab a completely new byte from this table. It acts as the complex, nonlinear heart of AES security. Now, why build it exactly like this? It all goes back to that multiplicative inverse in GF of 2 to the 8 we talked about earlier.
By taking the mathematical inverse and applying a really specific bitwise transformation to it, AES builds a massive nonlinear wall. You simply cannot linearly predict the output bits from the input bits. It completely scrambles any patterns from the plaintext data, which stops mathematical cryptalysis dead in its tracks.
All right, Section 4, Forging the Expanded Key. Let's pivot away from our data byte for a minute and look at the fuel that actually powers this whole thing, the key expansion used in the add round key step.
Say you start with a standard 128-bit key. That's literally just 16 bytes. But wait, we have an initial add round key step plus 10 full rounds, and every single one of those requires its own 16-byte key. So, AES takes that one short initial key and massively expands it into a linear array of 44 words, which is 176 bytes in total.
Let's actually step through the math here using table 6.3 as our chalkboard. To generate a new keyword, we grab the previous word and run it through a series of invertible transformations. First up, rotword does a cyclic shift, just sliding the bytes over. Then, subword pushes those bytes right through that exact same S box we just learned about. Finally, we do an exclusive OR with a value called archon, which stands for round constant.
Those round constants, or archon, they are absolutely crucial for keeping the encryption strong. Imagine if every round generated its keys using the exact same symmetric logic. An attacker could easily exploit that symmetry, taking just a tiny piece of a round key to deduce the entire master key. By injecting a unique, round-dependent constant into the mix, AES completely shatters that symmetry. Knowing one part of the round key doesn't give the attacker a free pass to the rest of it. Which brings us to Section 5, Reversing the AES Process. Our byte made it. It survived the rounds and is fully ciphertext now. But how do we logically reverse the cipher to rescue our original plaintext byte?
Notice the structural differences between these two. To decrypt, you'd think we just run everything backward, using the expanded keys in reverse order, right? Well, sort of. The sequence of operations isn't identical. Because the encryption transformations are applied in a specific order, their exact inverses have to be applied in reverse to undo them. Normally that means you'd need a totally different software architecture for decryption compared to encryption.
But mathematicians are clever. They found a brilliant workaround, which you're looking at right here, the equivalent inverse cipher. Because inverse shift rows only messes with byte sequence, and inverse subbytes only messes with byte contents, they are totally independent of each other. They commute. We can literally just swap them mathematically. By doing the same trick with inverse mixed columns and add round key, we create a decryption structure that follows the exact same sequence format as encryption. It's an elegant mathematical mirror, perfectly designed to extract our original byte.
As we wrap up this explainer, I want to leave you with a real brain teaser. We just walked through every single step. The algorithms are 100% public. The lookup tables are printed right there in your textbooks. So, why is AES still mathematically unbreakable today? It all comes down to computational complexity. The massive diffusion that spreads our data out, combined with that impenetrable nonlinear S-box wall, creates a literal fortress. Even when you have the blueprints, the computing power you'd need to reverse it without the master key far exceeds what modern technology can do. Thanks for joining me on this Bytes journey. Keep studying hard, and I'll see you in the next explainer.